The release of ChatGPT 5 and the utter failure that was Meta's AI smart glasses demo has left a lot of people feeling like LLMs and generative AI models have plateaued. From individual users to influencers and content creators to tech reporters and insiders, all have been discussing how these new AI models are under-delivering on the promises made by the companies that built them. People are even making the claim that we are starting to see companies move towards a more cost-saving approach to try to get some kind of return for their investors. I don't have any evidence that that was the reason why these models seem to be delivering so much less than what people expected. However, I do believe we have hit a plateau when it comes to how much generative AI and specifically generative text models can develop and grow. To lay out my initial stance going into this, I do believe that LLMs and generative text models have done incredible things and have shown real uses, from coders accelerating development to students using it to cheat on tests. However, I have never believed the more AI-forward people that generative AI will lead to an artificial general intelligence. For a long while, it was more of a feeling based off of my understanding of how these models worked that led me to believing that. But recently, we had 2 research papers get published, one from NVIDIA and one from Apple, and I finally feel I have the raw data to support what was a feeling I had about these models. So let's go through these 2 papers, and while doing so, I'll discuss why I believe these corroborate my opinion that LLMs will never be generally intelligent. First, NVIDIA's paper, titled Small Language Models Are the Future of Agentic AI. It focuses on agentic AI, which is the main way many AI companies are trying to expand the capability of their models. The idea is that by having several models, each focused on a specific task, the overall system is able to run more efficiently and with less errors or hallucinations. There are 2 types of models in this setup: a lead agent that takes in the user's language or text input and sends out commands to the second type, sub-agents that act out those commands. The main thrust of NVIDIA's argument is that the current setup of using large language models is not necessary, and to quote the paper, small rather than large language models are the future of agentic AI. This might seem like a small change, but in actuality, it's quite a massive one. Not only does this mean that the quoted $57 billion investment into cloud infrastructure for AI seems just like a massive waste of cash, it also calls into question the existence of models like ChatGPT. After all, if you can get everything you need from a model that can run on a personal computer and not across multiple massive data centers, what does ChatGPT actually provide to a normal user? But before we ask those questions, first we have to ask, how does NVIDIA support their claim? They have 3 main statements to support their claim in the paper. SLMs, small language models, are principally sufficiently powerful to handle language modeling errands of agentic applications, inherently more operationally suitable for use in agentic systems than LLMs, and necessarily more economical for the vast majority of LM language model uses in agentic systems than their general purpose LLM counterparts by virtue of their smaller size. NVIDIA provides a wealth of evidence to support these claims, along with an entire section where they put forward counterarguments to their findings and then rebut them. It really is a well-done paper that I recommend reading. But it's important to note, this paper is quite forgiving to AI models and their limitations, which makes sense. NVIDIA has become the most valuable company on the planet because of this recent AI boom. But that means if you are going to read the paper, do take the phrasing they use into mind. There are a lot of sections where NVIDIA deliberately uses softer language or otherwise downplays the extent of their findings, so be mindful when reading it. But even with the lighter tone they use, it is apparent that there are issues with the current use of resources to support LLMs. The first set of evidence comes from evaluations performed on these smaller models by the companies that test them. They provide several examples of SLMs outperforming LLMs, including Microsoft Phi getting evaluation scores on par with LLM models that are an order of magnitude larger while running 15 times faster, and DeepSeek R1 Distill outperforming Claude 3.5 Sonnet and GPT-4o. Another set of evidence they provide details on how much more economical they are. They have several measures of what economical means with regards to language models. There is inference efficiency, aka how quickly and accurately a model can respond to a given prompt, where they show that SLMs are 10 to 30 times cheaper across pretty much all measures compared to LLMs. Also, the adaptability of these models, requiring only a few hours to fix, add, or specialize behavior instead of the weeks LLMs take. Then there's edge deployment, which, while not specific to the model per se, basically means that because they are smaller, you can deploy them closer to the end user. And they round out their economic analysis with parameter utilization. With current LLMs, you have to train it on such a wide variety of topics and use cases. So you end up having a lot of nodes and parameters that just don't get used often, if at all. Compare this to smaller models, where a much larger proportion of their nodes and parameters are actually used. NVIDIA goes into a lot more detail, with a lot more evidence and argumentation to support their thesis. From allowing people to train their own AIs, which offers greater accessibility and can reduce systemic biases, to being able to have a wider variety in the types of agents that can be created. And they also go through what a transition from LLMs to SLMs would look like. Again, this is a really well done paper. But for the purpose of my thesis, that LLMs will never be generally intelligent, NVIDIA's findings lead to answers that pose different questions. What's the point of spending all of this time, money, and energy to develop these massive LLMs when a SLM is able to outperform, or at least be competitive with you at an astronomically lower cost? Why would anyone spend the billions upon billions of dollars investing into LLMs if you're ultimately going to be undercut by a SLM? And at an even deeper level, if the models are getting smaller and more focused for specific tasks, wouldn't a normal machine learning model do just as well, if not better? While a machine learning system can also get things wrong, a language model can hallucinate an answer that wasn't even in the list of possible results. If you ask a machine learning model to identify real animals from a picture, every once in a while it might call a horse a donkey, but a language model might call a horse a unicorn. And that doesn't even include problems that already have an algorithmic solution, like the Tower of Hanoi.
That's the rule of Chekhov's gun. Have a gun.
Now, some people would argue that LLMs still have their uses, which is a valid argument, and they believe that these models will not only continue to get better, but that after enough training, they will magically hit general intelligence, and then the world will end, or whatever sci-fi future they've dreamed up. But the paper by Apple pokes a rather large hole in this argument. The Apple paper, titled The Illusion of Thinking, Understanding the Strengths and Limitations of Reasoning Models via the Lens of Problem Complexity, not exactly bearing the lead in that title, is focused on comparing the reasoning capabilities of LLMs and their more trained and advanced versions, LRMs, large reasoning models, to gain a better understanding of the two's capabilities. They do this by moving away from the standard mathematical and coding test suites. These have been suspected for a while to be gamed by the AI companies, not even through any deliberate training by the companies themselves, but mainly through the prevalence of these types of questions in the training data, something that would be very difficult to weed out in the gargantuan amount of data that these models train on. So they developed a different set of tests that still have an algorithmic solution. In other words, it's a puzzle that still requires math, but is not necessarily a math problem. For example, one of the puzzles they gave to Claude 3.7, an LLM, and Sonnet Thinking, an LRM, is the Tower of Hanoi.
Chekhov's gun.
The problem looks like this. You have 3 pegs. On the leftmost peg, you have a stacked number of disks of increasing size, while the middle and right pegs are empty. The task is to move the disks to the rightmost peg, such that they form a tower, without having a larger disk sit on a smaller one. It's a pretty simple game once you understand the rules, so much so that you can give it to kids to play with and to computer science and math students to find the optimal solution for. You can also increase the complexity by adding more disks, making it a perfect test to see how these models scale. Apple's results from when 3.7 and Sonnet Thinking played this game are broken up into 3 sections based on the complexity. For low complexity, the LLM outperformed the LRM. This kind of makes sense, as the smaller LLM is more likely to take the first correct answer they see, while the larger LRM may be checking more answers. Then moderate complexity, where the LRM overtakes the LLM. Again, this is to be expected. That extra computational ability is coming into effect. But then we hit high complexity, where both the LLM and the LRM, to quote the paper, collapse. And it really is a dramatic collapse for the LRM, with it plummeting from around 70 to 75% accuracy to 10 to 15% accuracy, moving from 7 to 8 disks. From this and the other tests, Apple offers 5 major points they want the reader to focus on. The first and fourth points are just about how the current methods of evaluation would not catch these issues, but the real heavy hitters are points 2, 3, and 5. We show that state-of-the-art LRMs, O3 Mini, DeepSeek R1, Claude 3.7 Sonnet Thinking, still fail to develop generalizable problem-solving capabilities, with accuracy ultimately collapsing to 0 beyond certain complexities across different environments. We find that there exists a scaling limit in the LRM's reasoning effort with respect to problem complexity, evidenced by the counterintuitive decreasing trend in the thinking tokens after a complexity point. And we uncover surprising limitations in LRM's ability to perform exact computation, including their failure to benefit from explicit algorithms and their inconsistent reasoning across puzzle types. What they are saying with these 3 points is that even the most advanced AI models fail to develop a generalized way of approaching problems. But if you paid attention to points 3 and 5, they also stop using more tokens once the task is complex enough, and at no point show consistent reasons for their answers. This is not how you develop true general intelligence. This is more akin to when a student doesn't use a formula to solve a math problem, and instead just plugs and chugs with every possible number combination until they get a correct answer. And much like when a student does that, eventually the models just say, screw it. Here's an answer, test score doesn't matter anymore. And this happened with every game that Apple tried across 5 different models from 3 different companies. So this is not just an individualized issue with one company training a model wrong. This is fundamental to the very logic that undergirds these models. It gets even more damning when you reread the 5th point and see that Apple gives the LRMs the exact algorithm to efficiently find the optimal or correct solution in the prompt, and they don't use it. The LRMs fail to recognize the skeleton key they are given. The models are effectively throwing shit at the wall to see what sticks. Much like the NVIDIA paper, the Apple paper has a lot more information. Too much for this video to stay interesting, going in depth about the structure of the puzzles, testing environments, and concerns with the limitations of these models. And also, like with the NVIDIA paper, I would highly recommend you read it yourself. I have both linked in the description. Ultimately, the paper's findings provide the second point in favor of my thesis that LLMs will never be generally intelligent. There is no evidence that these models, even when designed for reasoning, actually develop an understanding of the problems that are presented to them. They seem fundamentally incapable of taking the first steps to true intelligence, recognizing a situation, taking into account the variables at play, and breaking a problem down into its component parts to be able to actually solve it, rather than blindly hitting the right answer after trying a bunch of random ones. Just shoving more data into a model doesn't work. This point, along with my previous point from the NVIDIA paper, combine to trap AI companies between a rock and a hard place. On one side, if you want to handle more complex and demanding tasks, the NVIDIA paper proves that the best option you have is an agentic structure, with SLMs as the lead agent, combined with either other SLMs, machine learning, or normal algorithms for the subagents. That being said, SLMs, although powerful, are ultimately limited by their size from ever becoming generally intelligent. On the other side, if you wanted to dump more resources into LLMs or LRMs, the Apple paper proves that they have severe computational limits, leading to questions of if that path is worth the exponentially increasing costs for a chatbot. And a chatbot simply will not give the returns needed to recoup the training costs, let alone give returns to investors. This means that unless a ton of billionaires give up all of their net worth to one AI company. There is no way to even attempt the massive amount of training LLMs would need, assuming that it could ever reach general intelligence. And that method brings me to a different thought. A thought about the way we are approaching AI itself, that ultimately makes me confident the LLMs will never be generally intelligent. When thinking about these models and how they are trained by simply shoving more and more data down their throats, my mind keeps coming back to a different, yet oddly similar situation. I'm reminded of a video that I watched a few years back, titled "Why Coco Probably Couldn't Talk, Sorry," by Soup Emporium. In the video, Soup describes the two competing schools of thought when it came to learning language. The first argued that humans have an innate skill when it comes to learning and developing language, and the other argued that language was simply about learning the rules and memorizing words, and so an animal such as an ape could learn how to speak if simply taught. And what that video goes over are the colossal amount of failures the second group had. Ape after ape after ape being raised in captivity, forced to either memorize pictures or gesture enough to get food, with the trainers constantly grasping at straws for any mark of true language, of true intelligence, with no ape ever achieving it. And I feel as though these AI models are similar to those apes. These companies are trying, through rote memorization, to teach these models language, and thus intelligence. They feel that unlike the apes, the models being not alive and able to be trained 24/7, that they will do what the apes could not. And much like the apes before, they get some information right. The apes were able to sign well enough for food, and the models can spit out a recipe. But neither apes nor AI models understand that the gestures they perform or the characters they type out mean the abstract concept of food or cooking, let alone the truly high-level concepts of politics, climate change, interpersonal relationships, or any number of ideas. The apes only learned that by pressing buttons in a certain order or waving their hands enough, they got food and attention, and the AI models simply calculate that outputting characters in a specific order gets a higher score on a test. The apes never understood language, and the AI models do not understand language. They are not intelligent. Does this mean that AI models are useless? No, quite the opposite. I think the NVIDIA paper shows that there will be plenty of real-world uses for specifically agentic models. I could very easily see a situation where a company uses a SLM to manage a suite of SLMs, machine learning models, and normal algorithms to handle multi-part tasks. But let's not get ahead of ourselves. The chatbots that people are using right now to avoid either touching grass or having to experience the great dismay of feeling kind of awkward in a conversation are never going to hit general intelligence, and anyone who says as much is caught up in the hype. And this becomes even more apparent when you dig into the arguments AGI supporters provide and find that a lot of their basis for AGI relies on some advancement for AI that will make it generally intelligent, which is just wish casting. Before the video ends, there is one side point I want to bring up. It's not really related to this discussion, but I don't want to make a whole video about it. And it involves a particular phrasing that people are using when discussing things like AI, AI training, and especially AI training with synthetic data that is AI generated.
This has the obvious upside of now you can make an unlimited amount of data, and the obvious downside of, well, if it's just training on itself, won't it just kind of like loop into this weird self-reinforcing thing where it becomes, it's no longer even responding to what humans want necessarily. It's like training itself to want what it wants, and it becomes farther and farther from this is a thing we made to it's making itself.
The AI models do not want, they do not feel, they do not have desires. Please stop using these words when discussing models. It may seem small, but I really do feel that using this type of language hurts people by enabling a level of personification to a dangerous degree. We're already having people go into chatbot psychosis. We don't need to be encouraging it. Thank you all for watching. Again, I would highly recommend that you read both of these papers. Neither are too long or too jargon heavy. If you have any other thoughts or just want to discuss, leave a comment. Thanks.